Good evening, everybody, and thanks for turning up. I was asked to give a bit of a presentation on a major study which has recently been concluded, which is the dispersion modeling study that is a detailed way of examining the contribution of sources to ambient air quality in the airshed. And what I wanted to do a little bit was to provide some background on what dispersion modeling is, what it can do, why it's a useful management tool. I'll talk a little bit about the current study that's just been released. There are hard copies available, so I won't go into incredible detail there, but because you can read the report yourself, but I'll talk about it a little bit. I'll compare it a bit with other studies that have been done, and then I'll look a bit at what the limitations are and what we need to do to be able to move forward in using the results from this study to effectively manage air quality, improve air quality here. I want to thank a few people. There's lots of people who were involved in this project. It's actually it's a research working group project. It started over 5 years ago. We had the first idea in our minds to do this. But John Spagnol was the modeler who's currently with Stantec, who carried the project through to completion and also started working on it in the early stages. And the research working group was involved in this intimately as well. It was really an interactive process where the research working group members were interacting with the modeler. And it was an iterative process where when we identified issues, we went back and forth a number of times. So a lot of people, especially Dennis Fudge and Dave Sutherland, who's not here right now, we're deeply involved in that process. So this is the outline for the talk. I'll be giving a little bit of background. I won't talk too much about the air quality issues here since we know about that already. I'll describe different kinds of source attribution methods where we try and ascribe sources to ambient levels. I'll discuss what dispersion modeling is, what it can do, and we'll spend some time looking at the current study, the Prince George dispersion modeling study, what its essential results are, what some of the limitations are, what we're doing now to meet those limitations. Two main air quality issues. The first one is odor, the second one is particulate matter. So particulate matter is the one that's of a major health concern. And so especially PM10, particulate matter less than 10 microns in diameter, and PM2.5 is of more concern. The odor is due to totally reduced sulfur levels. It's more of a nuisance issue, but it's not thought to be a primary health impact. Most of the work to date, including phase 3, which we just launched today, is dealing with particulate matter. That's the type of pollutant that's of most concern from a health perspective. We look at, this is PM2.5 over time, and what this graph is showing is from 1998 through 2008, these are called box plots. The little x's represent the average annual value for those 11 years. And the box represents the distribution. So the bottom of the box is the 25th percentile. That means that 25% of the values are below the bottom of the box. The top of the box is the 75th. The top of the whisker here is the 95th percentile. And the little dot at the top is the 98th percentile. And that means that 2% of the values exceed that, the 98% are less than it. And these are significant because the 98th percentile corresponds to the Canada-wide standard for particulate matter, and that value is at 30. So if we look at this over time, we can see there's not a lot of trend. There's a bit of a change in 2004, after 2004, but that is more likely due to a change in the way monitoring was done, due to a change in the actual monitor for particulate matter. It may not be an actual reduction. So PM2.5 has been no big trend in PM2.5 over time. And the BC ambient air quality objective for annual values is 8. So 8 is down here somewhere, and so we're hovering around, we're over 8 in terms of the mean. The x's here are over 8 most years, not every year. And the 98th percentile is often over 30. So we have elevated levels of PM2.5. We all know this. Well, when we think about air quality, we're concerned about ambient air quality. So the air quality in the air that you and I breathe, where people live, where people work. And so if we think about that, it's not just about the size of the relative sources, it's their contribution to the air that we all breathe. So it's the impact that's important. So when we think about the air quality problem, there are 3 components. There are the sources, so where the pollutants are being emitted. There's the atmosphere, which takes them from the sources and transports and diffuses and disperses them until it reaches the receptors. And the receptors are you and I. It's where people are, locations, geographic locations. We need to also consider, if we took this a bit further, the health impact on the receptors, so the relative health impacts. So we need to consider all three of these things. Since what we care about is the impact on receptors. It's not just source sizes that are important, it's how the sources get dispersed and transported. So if we have sources that are far away from receptors, then the ambient air quality that results wouldn't necessarily be problematic. If the sources are nearby, they could be. If the sources are a high elevation emission, then they'll probably be more diluted and dispersed before they reach the individual receptors. So we can't just look at the relative ranking of sources, we have to consider the other parts of the picture as well. And the dispersion model does this. It has sources, it has the atmosphere, and it calculates the ambient levels at receptor locations. So as we know, these are complex issues, and solutions will be challenging, especially in a problem like particulate matter, in which there are a whole host of sources, very many sources. We care about impact on people, and we care about ambient air quality. So the important thing is ambient air quality here for people living and working. In terms of air quality management, the goal, of course, is to lower the ambient levels. Okay. To do this effectively, we need to know which sources contribute to the ambient levels at a given point in the airshed. Right? So we need to know, if we want to reduce the ambient levels downtown, we need to know which sources contribute in a quantitative way to the ambient air quality at that location. And so this is source attribution. We need to attribute the sources to the ambient levels to the sources. And in doing that, if we know which sources are contributing and how much, we can rank them, and we can decide which ones are most effective to reduce to achieve our goals in ambient air quality. And that's really what the goal of air quality management is. So dispersion modeling is one such tool, and it's a very useful one, as I hope we'll see during this presentation, that will help us get at that goal. These are the kinds of source attribution studies generally. There are receptor modeling studies, and receptor modeling studies are based on ambient air quality data. So the levels that are observed in an airshed. One such type of study is a wind sector analysis, and Dennis Fudge has done something like, Dennis Fudge and Dave Sutherland did something like that, where we look at a monitoring location, the pollutant levels correlated with the direction from which the wind is blowing. And so you know that if there's a source to the north, which is the north is over here probably, it's a source to the north and you have high pollutant levels when the winds are from that direction, then you can infer that those high pollutant levels are coming from sources in that direction. This is a wind sector analysis. But it doesn't tell you precisely which sources are contributing, so it gives you a general idea. Other receptor modeling studies are things like chemical mass balance and positive matrix factorization. And these basically look at the chemical makeup on filters. So for particulate matter, you trap the particles on a filter, you analyze chemically what's on the filter, and then you relate, based on the chemical constituents on the filter, you find sources that vary together, and you relate them to particular source sectors. In chemical mass balance, you have to identify the chemicals emitted by specific sources. So a priori, before you start, you have to say, pulp mills emit these things, road dust emits this, people burning wood in their wood stoves emit that, and then you match up those profiles with what you see on the filters. And in that way, you can estimate the contribution of those major source categories to the particles that were collected on a particular filter. And PMF uses the same data, it uses chemical constituents on filters, but it doesn't assume that you have an a priori source profile. It basically correlates the chemical signatures on the filters with each other, finds the ones that vary together, and then then you have to interpret what source they would be from based on the chemical makeup. So all of these receptor modeling studies, they're based on ambient data. They can give you a general idea of what are the main source categories, but they don't really give you the kinds of specific information that you really want from an air quality management perspective. What you really want to know is which specific source do you need to tackle to improve the air quality in a given location. The receptor modeling studies will tell you in general what are the important sectors, what are the important categories of sources that are worth controlling, but not which specific source. They can't really do that. Dispersion modeling is the next major type of source attribution study that can be done, and this can get us at that kind of information. It's based on an emission inventory, so we need to know what the emissions are in the airshed. Meteorological data, so what the winds and the temperature and the stability is like, so how the atmosphere acts to take the sources and move them to the receptors. We validate them by dispersion modeling by comparing it with ambient data. And there are different types of dispersion modeling of varying complexity and varying sophistication. So some models are very simple, some are more complex. The more complex models generally give you a better solution. There have been several past studies. Dispersion modeling is a very common tool used by the consulting sector for doing environmental impact assessments, for example. If you want to build a new facility, you'll do a dispersion modeling study. You'll be required to do a dispersion modeling study before the facility is built to estimate the impact of that facility on the ambient air, for example. The current study we're talking about today, the study that was released by Stantec, is a very comprehensive study. It's using the model called CalPUF. So CalPUF is a very sort of a high-end dispersion model, a state-of-the-art dispersion model. It's very sophisticated. And I'll be describing some of the results from that a little bit later. So none of the methods that we have to attribute sources to ambient levels are perfect. They all have problems inherent in them, some kinds of problems. They have strengths and weaknesses and limitations. As I mentioned before, the wind sector analysis types of studies and receptor modeling can give general guidance, but can't draw a very specific link between a source and an ambient concentration. Dispersion modeling can make that specific link. So what the dispersion model outputs, you can look at a given spot in the airshed and say the model predicts an annual average level of 10 micrograms per cubic meter. You can break that 10 micrograms down at that location to the contribution from individual sources all in the airshed that are contained in the model. And so you can rank those sources and figure out which ones, by reducing or removing certain sources, what the impact of that would be on improving the ambient air quality. This is what we really need to do for managing air quality. Three components. All dispersion models have three components, as I mentioned before. Emission inventory is key. So the emission inventory lists all the sources, identifies what they emit, how much they emit, the characteristics of the emission, the temperature, whether it's an area source or a point source, the elevation of the emission. All that sort of detailed knowledge is needed to feed into the model. So we have to characterize all the emissions. For a problem like particulate matter, this is actually a very difficult thing to do because there are so many sources. If we were worried about a pollutant that was emitted by 1 or 2 or 3 or 10 places, it would be an easy problem. But because we have particulate matter is ubiquitous in the environment, it's emitted by many sources, it's actually a difficult problem to adequately characterize the emissions. And a lot of the work involved in developing the current model has been worked on this emission inventory, trying to refine it and improve the estimates. A meteorological model. So the meteorological model tells us in a kind of a three-dimensional grid what the winds are like every hour of the year, what the temperatures are like, what the stability or the thermals are like, and the mixing in the atmosphere is like. And all that information is needed to be able to carry the pollutants from the source to the receptor. And at the same time as it's carried from source to receptor, it gets mixed with fresh air and diluted. So that these are what the meteorological model does. And then finally, the dispersion model itself takes the emissions, puts them into the meteorology, and then calculates that dispersion, that mixing and dilution of pollutants that occurs, and keeps track of, at every given point in the airshed, which sources are contributing to the levels at that particular point. So this is what all dispersion models can do. So the link between source and ambient concentration at receptors is maintained as a key feature, so we know what the link is. And therefore we can use the model to account for and rank all the sources and their contribution to ambient air quality. And this is exactly what is needed for air quality management. This is the exact kind of information you need. So the key here is if you feel the model is realistic, it's doing the right things, and then you can use it directly as a tool to rank and prioritize sources. So we have to believe the predictions are right. We have to believe the model is doing the right thing. It's realistic. It's got a good handle on the meteorology. It's predicting levels which are comparable to what we observe at monitoring locations. We have to have confidence that the model is doing the right thing. Otherwise, any interpretations based on the model results may be flawed. So a large part of the project has actually been this sort of quality control back and forth iteration where John Spagnuolo, the primary modeler, would produce some results. He would present them to the research working group. We would all around the table examine them and kind of poke at them and prod at them and test them and say, this doesn't make sense, this does make sense, go back and look at that. So I don't know how many times we had a back and forth process, but dozens and dozens of times back and forth, and continually refining the model, both from the modeling strategy perspective, but